Hello, everyone. Greetings from England in this post-Brexit world. I hope everyone's doing well. I saw that there's about 20 or so people here. I'm impressed that you've managed to stick it out until the end of the week. Well done. Thank you. So I'm going to talk today a little bit about the code that I've been leading for the last, I guess, 20 years now. It's what's called a population synthesis code. You've probably heard a bit about these all week. A lot of people have spoken about them, and it really is like simulating a population. It's not a real population of people, it's a population of stars, of course. So today I will go through and say what we have done with this code in the last few years, and a little bit about what we're doing now, because we've got quite a few very nice, very good people working on this, and also the future plans. And I'm hoping that you can help me with the future plans, because we've seen many talks where we've got great ideas of physics, but we can test them out. So what is the stellar population modeling we're doing? I mean, I'm amazed that no one has tried to put a picture of the actual dynamic duo in their talk. Well, here they are with a state-of-the-art computer. The idea here is to go from this screen as you have at the top, these two panels at the top, where you go from real observations down to here where we have some simulations. And the idea is then to compare the two statistically and quantitatively, and to then pin down what the uncertain physics is. And there's a lot of uncertain physics in stellar physics, as we know. We've heard that all the last week. And the other thing is, of course, that the data has got bigger and bigger and bigger. I mean, we have Gaia and ESA. There's a whole session on Gaia, which you should download now and go and watch. But there's other things, LSST and SKA, all these things that will bring us a huge amount of data right up until now and into the future. And I think it will only get bigger and bigger as time goes on. And so we have to find the best way to get the value for money from all of that investment. And I should say value for money, hard disks are very expensive now, so that may not be value. But so very quickly, what we do is we calculate numbers of stars, essentially, and it could be a rate of things. It could be anything that you can observe in the sky. And it's a big calculation. We've got three sums here. The first sum is overall time. And of course, you have the number of stars is proportional to this S here. This is the star formation rate. That's obvious. You make more stars, you see more stars. That makes sense. The blue psi here is the input function. So that's like the initial mass function that goes into this. But in our case, of course, it could be for binaries. So you could have single and binary stars. We heard about triples earlier. You could have quadruples, all these things. So it's actually quite a big multi-dimensional sum. And then we have this final one in red, which is the delta function for the stars. And that is the star in a phase of interest? So if you're counting main sequence stars, this will be 1 in your phase of interest. And if you're not, then it's 0. And all of these are multi-dimensional sums. They're complicated. So your parameter space is huge. And so you need a fast stellar evolution code to do this, or you can consider a limited parameter space. Now we take the fast code option. And so hence we have this binary C code that I've developed, and it has a runtime typically of fractions of a second for a whole evolution of a star. So you can do 1 million stars in 12 hours, 24 hours on a modern set of CPUs. I've only had one student whose laptop actually set on fire, but that's the way it goes. So what was binary C until recently? Well, it was based on the SSE BSE code. You've probably all heard of Hurley's paper from 2002. That's the basics of the stellar evolution algorithm. But I've updated a lot of that. So we have thermally pulsing AGB models, which are based on very detailed models. And I've put in all the nucleosynthesis. So we have first, second, third dredge up, and hot bottom burning in low and intermediate mass stars. We have Wolf-Rayet stars in there as well. Type 2, 1bc, supernova yields. We can count gamma ray bursts as well. And it does a lot of the binary stuff. So we have the mass transfer. We have common envelope ejections, mergers, novae, type 1a supernovae, all these things that you could possibly want. And you can count up, all the chemical elements from these as well. And to give you a few sort of historical now papers on this, you've all seen this pie chart. I hate pie charts, but this comes up everywhere. I see it all the time. That's made using binary C. Nobody knows that because you don't read the paper, but you do steal the pie chart. Don't blame you. That's how it works. We've looked also at supernova rates. There's a few papers on that about how binaries affect the supernova time delay functions. A couple of years ago, we had a very nice paper out on stars being kicked out of the galaxy. These are the very fast hypervelocity stars that are escaping the galaxy, and how we make those as well using supernovae and binaries. That was really interesting stuff. We coupled it to an M-body code, so it's very easy to do. And we can also compare detailed, from spectroscopy, we can compare detailed chemical abundances to stars that are observed. This is a halo carbon enhanced metal poor star, for example. And this is all very straightforward stuff for us now. But now we're updating it. We're doing, I mean, we've been doing for many years actually what people are trying to do, which is to put in grids of models instead of using fitting formulae. And this makes sense because computers are faster and we can do this now. So Giovanni Maru, who's working with me in Surrey, he's making a new library of these models. They're based on Mesa, but they could be based on any code. It doesn't matter that it's Mesa. But what's fantastic is that fortunately, the old BSE tracks actually agree very well with Mesa here. You can't see them because they're hidden at the low mass end down here. But as you go up to the top, you see they start to diverge, and the BSE tracks aren't really valid for greater than 50 solar masses. So people that use the BSE code or its derivatives like M-body 6 are just extrapolating at that mass. Whereas what we've done is actually construct models. Now we can use any model grid here. Please, if you have your model grid, you want us to use it, we can plug it in. It's not difficult. It's really we've written a specification for it. It's very easy. But we can go up to 300 plus solar masses before Mesa dies. And that's Mesa's limit, not ours. So what he's done, he's been using this to look at, for example, here, tides in tidal circularization and synchronization in clusters. This is, you can see the blue colors here and the green. This is his models to match the red points here. And he's constructed a whole statistical test for how you can actually model these. And you find that the only way to do it is to use the more detailed stellar structure and detailed tidal coefficients in Zahn's theory. If you don't do that, you use VSE, it doesn't work. If you only change the input distribution, so that's the distribution of eccentricities and periods, that doesn't work either. So the blue curve here is the KS test distance between the two populations. So the blue curve is the old code, and the yellow curve is the new code. And against itself, it's a self-consistency test. That's what you get here. That's just the Poisson error, really, from the counting. So it fits much better. I'm not saying it's a perfect fit, but it is better. We've also got a module to do triple stars. You saw a talk on that earlier today. This is with Tom Comerford, who was my student a couple of years, or last year, finished last year in Cambridge. And we can do all the triple star stuff as well. This is stuff I think that still has to be worked on, of course. Everything is work in progress, but this is certainly something I think we can use. And if anybody's interested in using this, we can certainly do it. I have several students working with me in Surrey. I want to tell you what they're updating. Well, Natalie Rees is working on the AGB models and also merge star models, doing those in some detail. The reason for this is that I think with Mesa, we can do this much better than we did in the past, with a much more complete set of stellar models. In the old days, it was 5 or 6 different models, 1, 2, 3 solar masses. We can now run them in between, which is fantastic. But we still got the same problems with convergence in Mesa. So if anyone knows how to fix that, let me know. Armin Ayapur is working with me. He's doing novae in the hope of eventually getting to type 1a supernovae. We're modifying Mesa to make it actually do novae properly and do it self-consistently with modeling based on 3D simulations, which is great fun. Everyone likes to blow up stars, right? So it's great fun. And David Hendricks is working with me on looking at several things to do with circumstellar disks and mass transfer. He's also doing stuff on pair instability supernovae and black hole mergers. So this is what we get for our black hole merger rate as a function of total mass. And this is the kind of statistics that we can now make quite routinely. We've also put in with Sophie Dykes, who was one of my students last year. She was a bachelor student doing a project on this. Very easy for bachelor students to use. I'll show in a minute. Looking at putting in the Moen-de Stefano distribution. So if you change from using just straight the Kruper with the normal flat Q distribution and stuff like that, the old-fashioned way, and you switch to theirs, you actually lower the rate of the black hole mergers, which is, I mean, it's a factor that's similar to the factors we were seeing triple through today. So. And stuff that I've been working on, I don't want to push my work too much, but Adam Jamin's been helping me with this. We've been doing circumbinary disk models, and I've written a code to do this, and you can make a circumbinary disk in a few seconds. It's very easy to do. So we've looked at the parameters that go into the disk. This is the alpha in the disk, the standard alpha prescription for viscosity, tidal strength. Here we have the mass and the angular momentum, and we can fit these to the disk you saw earlier, the IRAS telephone number disk. I can never remember which one it is. But we can fit that, and we've got all these all these observational parameters, and we can actually get a pretty good match with the observations with a model that runs in just a few seconds. You compare that to a radiative transfer model, which takes maybe an hour to make, and then has no evolution in it, whereas we have the full evolution of the disk. So Now, to go on to what other people have been doing that's new, Alex Kemp has been looking at nova rates. He's working in Monash. He took the code and he looked at how many novae we make and what are the properties of novae. This is something we can now do very easily because I've completely reworked the evolution algorithm in the code, so we can now detect each nova as an event in the code, which is a fantastic way to do things. Other people that are doing this, Nina Sartorio is doing population 3 X-ray binaries with this, with our new MINT library with the zero metallicity stars, very easy to do. She's looking at how we reionize the universe. And we've also been looking at neutron star mergers as a function of the common envelope parameters, which is, it's a test worth doing for sure. And so hopefully that paper will be out soon. It's with Alex Tanaka in Oxford and Avishai. If he's still on here, I don't know. He's probably not at the moment. We can also do full nucleosynthesis in all of these, which is why they're so useful. This is a plot showing thick disk apogee stars, those are these points, as a function of mass here and carbon to nitrogen ratio. So this is stars that have first dredge up. And you see most of the stars sit here, but we have these weird stars out here, which are the red stragglers. Now those we think are merged stars. And actually we've calculated some statistics for these, and we calculated binary fractions and things like that. So they're very useful because we can compare them to the stars that are in Kepler. So it's extremely handy stuff. We get the statistical numbers, which is the whole point. Now, if you're interested, I'll put all this on the Slack afterwards. We have a website with full documentation. All the codes are on our GitLab. If you want access to that, drop me an email. It can be sorted instantly. We have a Slack channel for 24-hour support. There's an online interface. If you want to play and you want to make your own binaries, just go there and plug in the numbers and see what it does. A lot of people have used that in the past, and some of it gets published, which is quite amazing. We have a Twitter feed, which sometimes I use, so that's quite fun. And there's also a YouTube channel with lots of tutorials. And indeed, I'm hoping to put this talk on there later on. Just search for binary C. Please don't type in this ridiculous URL. If I get 100 people sign up to it, I can change it to binary C. Please do sign up. It'll be great. Now, if you want to put binary C into your code, this is very easy to do. We have an API, programming interface in C and Fortran, if you really want it. I'm not a Fortran person. I don't like it, but you can use it in Fortran if you want. It's fine. It uses the Meson build system, which is state of the art. Many projects now use this. It's extremely fast and also cross-platform. And there's a Python front end, which David Hendricks has written here, where all you have to do is type in pip install binary C Python, and it just works, which is great. But if you need David to help you with that, please just ask him. He's a lovely guy. And I think probably one of the biggest things we've done recently is to change the output. So there's a standardized form of output. So everything that comes out now in the populations, we have a population ensemble where all of the things go together. So the rates, the chemical yields, everything goes together. And it's in what's called JSON format, which looks like this, which is easily readable by computers. You can have nested data structures. It's fantastic. It's used very much by Python, for example. I use it in Perl because I'm old and Python didn't exist when I started, but that's fine. You can load it into pandas, plot it with Seaborn with one command. It's dead easy. So that's really useful. And these kind of things I'll be publishing in the next year or two, so we can use them. We have software which you can just go straight through, and it interpolates this, it interprets it for you and makes your plots with a few clicks. So it's very, very easy to get science out very quickly. And I think that's one of the great things about this. It also can make plots like this. This is the yields as a function of time of carbon-12 for a given set of physics. You can split the yields according to the stellar types that give you whatever they yield. So many different types of supernovae, the AGBs, the giant branches, common envelope projections, all these kinds of things. So if you're interested in the yields of chemical elements, we can do those pretty simply. Now, I know we're short for time, so I'm going to finish very soon. One other thing that I think binary C does very well is that we have interfaces for it to do outreach. Now, the top one here is by Tom Comerford. He wrote a 3D interface for it. So you can zoom in and spin around, and you can see the stars transferring mass. You can see them explode or form planetary nebulae. It's fantastic. It's really fantastic. It's a great tool. I would really urge you to try that. I think his website's off-site and offline at the moment, but I can send you a copy of the code. It's not a problem. The other thing we have is Window to the Stars, which I wrote many years ago. I keep upgrading. This is a stellar interface, so you can run stellar evolution codes with a graphical interface, like a web browser for stars. Now, we've been using this recently in a Stars for Schools program, so I've had secondary school students actually making stellar evolution models and really learning about stars. They love it. I'm amazed how much they love it. I didn't expect it at all. I thought they'd say, oh no, it's too complicated, but they are really into it. They're trying to reprogram it and everything's fantastic. We do all that on Raspberry Pis, by the way, so it's really fast, really cheap, and people even from not too wealthy backgrounds can then have an opportunity to go away and try these things out. Now, I'm giving a couple of lectures on this at the Impress School in Heidelberg later this year. So if anybody wants to learn more, I mean, we've got the YouTube channel, but then I'll be giving these actual lectures as well. So if you want to learn a bit more, we'll be putting some virtual machines together for that, and I'll put all those online as well. Okay, so there's some upcoming improvements. We're hoping to improve how we do the interpolation in our MINT library. This is because it's difficult to interpolate sets of data from stellar models. They're a real pain because they're not square boxes that you can interpolate in. So we're trying to do that with machine learning, and I think that's got to be the way forward. It's how a lot of people are doing these things now. But we're also upgrading the physics in it. Remember, we can use any stellar code, so if you have a favorite, we can put that in. I've also put in planetary objects, so you can have orbiting planetary objects. It's really easy to do. It's not such a challenge, to be honest. I think the big challenge is going to be Bayesian and MCMC type data processing, because the statistics are improving a huge amount these days, and I think this is where we have to go next. But we keep fixing up the online teaching and user interfaces so that they are more usable, they work better for people. And if you have any comments on those, I'd be very welcome. Please just send them to me. And of course, are there any new ideas from you? If you have new physics you want to test in here, I've spoken to a few of you on the Slack this week, which is fantastic. If any of you have any ideas, things you'd like to try, it's a very fast way to do it. And you can also cover a very large parameter space. And the problem with using a detailed stellar code to do a lot of these things, sometimes you need that. We understand that, that's absolutely fine, but often you don't. And if you're pretty sure you don't, this is a much more efficient way to do it because you can cover a large parameter space very quickly. Great. I think am I on time? I might be the only speaker that's on time. Maybe early. Maybe there are questions.
Okay. If you are in, thank you. We have a question from Michelle Montgomery. Does your code give us insight into evolutionary stage of massive stars, such as wide object like Wolf-Rayet stars, or figure out how subdwarf populate the HR diagram?
It can certainly do subdwarfs. That's not a problem. So with the new MINT library, we have the internal structure of the stars at each point. So what you can do is you can interpolate the temperature and density as a function of central hydrogen and mass of the star, which is a very good approximation on the main sequence. And then we can do the nuclear burning actually on the fly. So if you just want, I mean, it's very easy on the main sequence, it's PP and CNO, that's what we care about. And if you want to evolve a couple of stars on the main sequence, it takes a few seconds with full nucleosynthesis on the main sequence. Post main sequence we're still working on. It's a little more complicated, of course, always, but I don't think it should be too difficult because it's relatively straightforward on the red giant branch. You've just got a burning shell. The AGB is also relatively straightforward because again, you've got a burning shell and a mixed envelope. And core helium burning, I think, is also relatively straightforward. The more massive stars will be more of a challenge, for sure. But I think not impossible. So I think we could make plots like you saw in the previous talk in just a few seconds. Shouldn't be a problem at all. Because there's only a few burning chains that really matter, right? So it's triple alpha and alpha capture on carbon and oxygen, and that's about it for the energetics. So that's all you care about, really. And if you want to put the minor chains in there, the minor isotopes, you can put those in. It's very simple. So I think we could do that relatively straightforwardly, given a grid of models. The problem really is actually finding a way to interpolate those models. And I'm sure we'll hear in the next talk, that's not easy. So, or not easy to do reliably. And the way old codes like BSE worked was to use the time as a variable to control everything. So if you know the BSE code inside, it's got all these weird time coordinates. We try to use physical coordinates. So for the main sequence, we use central hydrogen abundance as the coordinate that tells you how evolved the star is, because that's really what a star thinks. It's much more physical. So we're trying to step away from the old way of doing things, but it takes a bit of time. At the moment, they're coupled, so we have BSE running at the end of MINT, but each time we put in a new piece, we improve.
Okay, thank you again. If there is any questions, if there are any questions, let us go to next talk. It will be